Hi everyone, in this video we are going to discuss natural causes of ozone depletion. So back in the 1970s, a group of scientists got together and they decided they were going to do everything they possibly could to measure the ozone concentration every single place on the planet Earth. So that means Texas, it means Michigan, it means Russia, and it means the North and the South Pole. So what's really interesting is that everything followed the classic pattern. So about 200 to 250 Dobson units for the equator, somewhere in between the equator and the poles, it was anywhere between 300 and 350. If they were in the northern atmosphere, so the northern latitudes, they could even have measurements all the way up to 400 Dobson units. But what was so weird is they started doing measurements of the South Pole, so let's make sure we're all on the same page here. South Pole, when I say the phrase South Pole, I mean the Antarctic. I've had problems with that before, so let's make sure we all are on the same page. We're not talking about different places there. In the South Pole, we're talking about the Antarctic. They actually got freaky small measurements of anywhere between 200 Dobson units all the way down to maybe even 83 Dobson units. So this teeny, tiny amount of ozone all hovering over the South Pole, which we now call the ozone hole, right? The hole in our ozone layer. So this measurement was so bizarre that these scientists actually thought their instruments were broken. They were like, oh, my instrument's broken. There's no way that has 83 Dobson units. Turns out it was correct. And so we wanted to figure out, more importantly, they wanted to figure out what was going on. How is this possible that over our pole for our northern side, we can have measurements all the way up to 400, but for our southern side, they're so small, they could be even lower than 100 Dobson units. So this was bizarre. They were freaking out. And so they started to measure everything they possibly could for the southern pole in terms of the Antarctic, especially in terms of their ozone concentration. So let's look at this graph here. For our y-axis down at the bottom, we have our year. So we're plotting all the way from 1980 all the way up to about 2011 here. Where on our y-axis, we're actually talking about our concentration of ozone, but the minimum. So this is the lowest the concentration of ozone got for that year, starting in about 1980. So for example, in 1980, we saw that it had a concentration of 192 ozone Dobson units, where in 2006, it was actually as low as 83 Dobson units for the concentration of ozone. So in 2006, over the South Pole, we actually saw this teeny amount of ozone exist. There was a huge hole. So these scientists could not figure out what was going on. They're like, what is happening? So they started diving really deep into our ozone concentration. How do we make it? How do we break it? And what they found is that we have two very common or natural causes that we can break down ozone with. And the first one is our good friend water, which is sad because we absolutely need water, right? And we know that it's constantly in our atmosphere in this big cycle. So what happens? Water, H2O. When water is in our stratosphere or up in the upper atmosphere and it interacts with UV radiation, it actually can break apart into a H radical and an OH radical. Now, what is a radical? A radical is just represented by a tiny dot, but essentially it is something where you have one electron and it is unpaired, so it is not in a lone pair. If you recall, when we were looking at our Lewis structures or our symbols, we would always try to put our electrons together in a lone pair because one electron by itself is extraordinarily reactive. So when you see the word radical, I want you thinking reactive or unstable. And so what's really sad is these different pieces or these radicals, when they come in interaction, so this one, or I'm just going to say this here, when they come and they interact with ozone, after many steps, and I don't expect you to know the steps, it eventually forces ozone to decompose into diatomic oxygen. Okay, so we break apart ozone naturally just by water in our atmosphere. The second most common thing is with nitrous oxide. Now, nitrous oxide, which is N2O, okay, also, very common in our environment. We have a nitrogen cycle. We'll get into that later on in the semester, but it's very common. We actually want this to be in our atmosphere. It's fairly good for us. But unfortunately, again, when N2O interacts with monatomic oxygen, what we see is it breaks apart into two more radicals. So radical NO. Same thing as with water. When we create these radicals and they interact with ozone, through many steps, they break apart and they end up with diatomic oxygen. So we have two very common ways to break apart ozone, and they're things we don't actually want to change about our atmosphere. We need nitrous oxide in our environment, and we need water in our environment. And so these are just two of our very common ones that we talk about when we say our natural causes of ozone depletion. So let me ask you a question here. In September, Okay? When Antarctica has the largest hole, and when I'm talking about hole, I'm talking about hole in the ozone layer, okay? The question is, does it have a high or low UV index? Think about this carefully, okay? Good luck, guys. Take care of yourself.